Considering electromagnetic induction, here we have a coil of wire. In this case we have 40 turns in that coil of wire, and we have a magnet which we're going to bring towards the coil of wire. So imagine the field lines or lines of flux around the magnet going from north to south. As I bring the magnet in, you can see whilst the magnet is moving towards the coil and when it's moving away, you can see a deflection here on the voltmeter showing that a voltage or potential difference, more accurately, is being induced, there's a key word, across the terminals of the coil here and here. As I bring the north pole towards, the needle is deflected to the right. Notice that when the magnet is all inside the coil, even if it's moving, there is no induced potential difference. As we leave, notice as it came in, it was deflected to the right. As we leave, it's deflected to the left. So if we then look at the induced poles, remember from your electromagnets, if you have a current flowing through a coil of wire, then you have a magnetic field around it. It behaves like a power magnet. So let's look at the induced poles as the magnet moves. North pole coming in, it's induced as a north pole. So watch as the north pole comes in here. So this is becoming a north pole as the north pole approaches. Look what's happening here. As the south pole leaves, this becomes a north pole. So as it's coming in, a north pole is induced, which is trying to push it out. As it is leaving, the pole is induced to attract it back in. Watch. So here it's trying to pull the south pole back in, and then as the south pole comes in, the south pole is induced trying to push it out. So what you have here is the induced potential difference is being induced in such a way as the current which flows tries to stop the change causing it. So the change that's causing it is, in this case, the south pole coming in towards the solenoid or coil. So this end becomes a north pole, sorry, a south pole trying to push it out. So as the south comes in, we have a south pole here. Then we have nothing inside here because there is no cutting of field lines here, no change of the field through the coil. The entire field is in the coil now. There is no change of field through the coil. And then as we come out, well, it's trying to pull it back in. As north pole comes in, it becomes a north trying to push it out. And then this other end becomes a north trying to pull the south back in. So the first thing to notice is that this induced potential difference, induced voltage, induced EMF, we would call it at A level, is induced in such a way as to oppose the change causing it, in this case the movement of the magnet. Notice also then that if we vary the speed of the magnet, so let's go automatic again. If we have a speed of 4 units, see the maximum deflection is about 1.5 plus or minus. If we go for 8, it's about 0.3 plus or minus. So the speed of motion of the magnet, the rate of change of the field through the coil, how quickly the field is changing. And again, notice that when we're in here, there is no change in the field through the coil, and so there is no induced EMF, no induced potential difference, no induced voltage, whichever way you want to describe it. EMF at A level, potential difference better at GCSE, voltage if you must. So there is no change in the field here. The entire magnet is inside the coil, and so there is no induced EMF. If we change it faster, we get a bigger induced EMF. Let's also then increase the number of turns. So let's start with 20 turns, and let's go with our automatic, and let's go with as fast as we can make it. So there we've got about 1.5 volts again. Let's go for twice as many turns. Now we've got about 0.3 volts. So the number of turns in the coil is changing the rate of change of the field through the coil. Now at A level we talk about this as being flux linkage and the rate of change of flux linkage, where the flux is the word we use for the field lines around the magnet, and flux linkage is the flux times the number of turns in the coil, and the induced EMF is the rate of change of that flux linkage. So if we increase the flux linkage for the same speed, we're increasing the rate of change of flux linkage as the magnet moves through, and so we're increasing the induced EMF or potential difference or voltage, whatever level we're talking about. So you see the interesting shape of our induced EMF here, where we get a peak positive or peak negative value, but we get this flat spot as the magnet is wholly inside the coil.